have a fun thing. I'm actually giving you the derivative and asking you to find the critical points of the original function.
So that's
of x.
that's already the derivative
It's
that we're looking at.
already the derivative.
Like most of the work is done.
I know. You don't even have to take the derivative. So to find the critical points, I just want to see when the derivative, the slope, equals 0 or is undefined. So let's start by setting this derivative. Did I mention this is already the derivative?
That is a derivative.
Yeah.
I think you mentioned that.
Okay. Equal to 0. All right. Fractions are always annoying, so let's just get rid of the fraction. Or you can just use logic. For those thinkers out there, what x value is going to create the 0?
I'm thinking just 0.
Yeah.
I mean, why go through any fancy algebra?
Yeah.
I mean, it's pretty obvious.
6 times 0 is going to create 0 in the numerator. That's the only way you can get 0. But if you like doing algebra, you can just multiply both sides by the denominator, right? Then you have 6x equals 0, and so x equals 0. So that's one of my critical points. But now I have to go back and figure out where is the slope undefined. As soon as you see a denominator, you have to be suspicious. Remember, we cannot divide by 0. That's just craziness. Again, we could do some algebra, but why bother? Let's just analyze that. Let's look there. What x value is going to create a 0 in the denominator? I think
A 3?
A
Are
3.
you waiting for me to answer that,
I
Mr.?
was.
Okay, a 3.
a 3. Well done. Yeah, 3 is going to create a 0 in the denominator. Therefore, when x equals 3, we have an undefined slope, which means that's also a critical point. So far, so good?
That looks great.
Now, let's see which of these is a minimum or a maximum or neither. So let's come on over here and we'll do our little sign analysis. It's amazing how we do things alike, Mr. Haas. Great minds, I guess.
Yeah,
All
well.
right. So let's plug in -1 into my derivative. Let me just write it again here. And you know what I like to do? When I have rational exponents, when I'm doing stuff in my head, sometimes I just rewrite it as a radical. So that's a cubed root of x minus 3 squared. Sometimes that just helps me figure stuff out. So if I'm plugging in a -1 in for x, 6 times a -1 is going to give me a negative in the numerator. -1 minus 3 gives me a -4, but in squaring it, so I'm going to have something positive. Cube root of something positive. Negative divided by a positive, so I have a positive slope of my original function. Let's plug in 1. I've got a positive in the numerator. 1 minus, do I even have to go through that?
I'm thinking pretty much anything squared is going to give you a positive.
Anything squared. I think I'm always going to have a positive come out of that denominator. Positive divided by a positive is another positive slope. So far, so good? When I plug in a 4, oh, wait, this is a negative slope.
Oh, wow.
Negative divided by a positive is a negative.
Got right by me, Stuart.
Shucks.
Yeah,
I
sorry.
knew something was wrong. Okay, so let's go back. Negative divided by positive is a negative slope. Positive divided by positive, positive slope. I'm plugging in a 4. I have a positive in the numerator and a positive in the denominator. Positive slope.
Terrific.
Okay, so I've got a negative slope, then a positive slope, and more of a positive slope. It looks like I don't have any maximums, but I think I'm going to have a minimum. Just for fun, let's see if I can sketch this bad boy here. It might be a little tricky. Is that all right to say bad boy on
Absolutely.
the video? Okay, so I have a negative slope, and I always want to now keep in mind when x is 0, I had a 0 slope, right? Of my original function. When x was 3, I had a undefined slope. I always like having that in mind when I'm making a sketch. So I'm negative slope, nice 0 slope, positive slope. I think I can handle that. That looks pretty good. Now I'm getting to an undefined slope when x is 3, and then a positive slope after that. So, gosh, I'm not quite sure. I mean, undefined, I sometimes have either a jagged thing like that, or I can do one of those fun things. Which one is it going to work here, Mr. Haas? What do you think?
So those are pretty much your only choices. Undefined has either got to be like a sharp corner or vertical. I mean, that's really all it can be. And I'm thinking in this case, since it continues as a positive slope, it's going to have to be that vertical line.
I think you're right. Let's see if I can pull this off. There we go. A little vertical moment. Okay.
And that's it.
So here's a critical point, which is also a relative minimum. This is a critical point at x equals 3, but neither a minimum nor a maximum. And there we go.
So let me just ask, just to be clear here, if that last plus on the right-hand side there, if that had been a minus, right, let's pretend then it would have been the sharp corner
Would have been a
case.
sharp corner. That little guy would go up like a little teeter-totter sharp corner and then come down.
And you know for sure that can't be a zero slope. It could not have been like a nice smooth curvy thing because you know, in fact, at 3, the derivative is undefined.
Yeah. So you have to do some thinking when you're doing
That's terrific.
this. Thank you.
All right, we're having some fun
We
now.
are having fun.
This is really as good as it gets. So how did you spend your vacation, Mr. Haas? Well, I was looking at derivatives and, you know, sketching functions, curves of functions, yeah. So here is a second derivative. We've already taken the derivative and the derivative of the derivative. So here it is all laid out for you. This is the second derivative of some function. And as you know, the second derivative tells you about concavity. So all I'm going to do is look at the concavity and see if I can find the inflection points of the original function.
Very
This
good.
is really all about, sometimes students get that mixed up. We're using the derivative to find the slope of the original function and sketch the original function. We're using the second derivative to find the concavity and find the inflection points of the original function. This is not the inflection points of the second derivative.
Right.
It's the inflection points on the original function.
You got it. You
Right?
taught.
That's right.
Well
So
done.
all I need to do is figure out where this guy is either 0 or undefined. I can see it's not going to be undefined anywhere. There's nothing in the denominator. So I don't even need to write this. I'm just going to do this.
Just dive in.
I'm just going for it. I mean, I can see that I have 3 terms, nicely factored. I know what makes this first guy 0. Stick in a 0, makes it 0. Stick in a 1, that makes 0 squared is 0, of course, so x equals 1. And the next guy, a -3. -3 plus 3 is 0 to the 1/3 power, 0. So x equals -3. Are these my inflection points?
I don't
And
know.
who knows? Again, if this were the first derivative, which it's not, these would be guaranteed critical points. But this is the second derivative. These are places where the second derivative is 0. I don't know if they're inflection points or not. These are places that have no concavity, but I don't know about inflection points. So I'm just going to put them on my little number line here.
Because an inflection point is a change in concavity.
That is correct,
Not
Stuart.
just where there's a 0
That's
concavity.
fabulous.
Yeah. I should
let's
go
see.
into this teaching business.
So yes, those are my
Oh.
3 points. Now I'll just pick points in between. I have a -4. Stick it in for this x. That gives me a negative. This is going to be easy. -4 minus 1 is negative, but I really don't care because I'm squaring it. This guy's always going to come out positive. Something squared is always positive. Negative times positive. Put in my -4 here. That gives me a negative, but now I'm raising it to the 1/3 power. Well, what does that do? What's really the 1/3 power? What's the cube root? If you cube root a negative, it stays negative, of course. If you cube root a positive, it stays positive. So I really don't even have to pay attention to this exponent either. I put in my -4 and I get a negative, and negative it stays. Negative times a positive times negative is positive. You got to check my work.
I'm checking. It looks
All right.
beautiful.
I'll pick something in between -3 and 0. How about a -1?
Oh, wait. You already picked. Oh, nope. You're right.
All right, I'm doing
See,
all right?
now I'm screwing
All
up.
right.
That's perfect.
Don't mess me up. Put in a -1 there. That gives me a negative. Again, something or other squared is going to be positive. This will give me a -1 plus 3 is positive. So the 1/3 again stays positive. Negative times positive is negative. Put in a half. Positive, positive, positive.
Positive.
I'm pretty positive that's going to be positive.
That was good.
Yeah, thanks. Last one. I'll put in a 2. Positive, positive, positive. Again. Positive. So this is a very rough sketch. The function is concave up here. It's concave down. It's concave up in this region, and I do in fact have 2 inflection points. The inflection points occur when there is a change in concavity. So my inflection points are, I abbreviate, inflection point at x equals -3, and I have another inflection point at x equals 0, and at 1, it's concave up on both sides. So this is a place of 0 concavity, but it is not an inflection point.